vertex go over 4, because that's the next x value, and up how many? 2. And those will be your 3 points. Does everybody understand that? All right, so let's look at this square root function right here. And I just want to talk to you about it in different ways. So the parent function would look like this: 0, 0, 1, 1, 4, 2. Does everybody agree? So let's talk about the 2 out front first. You already did this one for homework last night, so we all should know this. What does the 2 out front do? Stretches it by 2. So y'all look, did we shift this one at all in number 11? No, we didn't move it left or right. We didn't move it up or down. It's staying at 0, 0. We're just stretching it. So the first point is going to stay at 0, 0 because I didn't shift it. But then instead of going over 1, how many am I going to go up? 2, because the a value is 2. So do you see how it's going to be taller? Because we are stretching it, right? So I do agree with Sean. It is kind of common sense. We're going to go over 1, up 2 this time. Not yet. I'm just dealing with the 2. I'm not dealing with the negative. I don't want to overwhelm anybody. We'll flip it in a second. So now I want y'all to look at the third point. It goes over 4, up 2 for the parent function. How much do you think it's going to go up now that we're stretching it by 2? I'll ask again. Y'all talking about something. It's common sense. Some of y'all ain't even paying attention to me. I can see it in your eyes. You just like halfway listening. A parent square root function, when it goes over 4, it goes up 2, right? Because the square root of 4 is 2. I'm stretching this one by 2. So instead of going up 2, how many do you think it's going to go up? 4. How'd you get 4, Henry? Not add 2. What's the 2 doing to the square root? Times 2. So really, when you're stretching it by 2, you're multiplying the y's by 2. So everybody look, when I go over 4 for this next one, it's going to go up 4 because I'm stretching it twice. I'm multiplying it by 2. So this is what the graph of 2 square root of x would look like right here. People at home, what questions do you have about that? Because I'm sure there are some. And I would much rather you ask now while you have them than hold on to it all day and wait till later. You got it? Makes sense? You just multiplying by 2 because it's stretching by 2. So instead of 0, 0, 1, 1, 4, 2, it's going to be 0, 0, 1, 2, 4, 4. So you're multiplying by 2. 0 times 2 is just 0, so it's going to stay at 0, 0. Now, I want to go to what Henry said since y'all aren't asking me any questions. Our equation up here, I'll find my good pens. There they are. Our equation up here says negative 2 square root of x. So we're stretching it by 2, and then what are we doing with the pink graph? Flipping it, reflecting it, right? So really, I would go over 1, down 2, go back to the vertex, over 1, 2, 3, 4, down 1, 2, 3, 4. So this graph right here, I'm about to highlight it. This is what our graph should have looked like when we graphed it in Desmos. Y'all okay with graphing number 11 by hand? Boy, always late. Y'all okay with graphing number 11 by hand? Yeah? Some of y'all ain't paying attention because you're like, I don't need to know this. I'm going to use Desmos. And then you're going to be screwed in Math 3 and Pre-Cal, for lack of a better word. So pay attention. I'm also going to give you an extra credit question on the test where you have to graph it by hand. Everybody's ready? All right, let's look at number 12. If I asked you to graph number 12 by hand, is this one going to start at our usual 0, 0? Why not? Because it did what? It went left 6. Very good. So y'all listen, where's the vertex of this square root function? Negative 6 what? 0. Good. So everybody look, this one is going to start at -6, 0. Now, am I going to go over 1, down 1, over 4, down 2? Why not? Hang on. First question, why am I saying down? Because it's negative. Good. And now why are y'all saying it's not 1, 1, 4, 2? Good. We're stretching it by 3. So my people at home, pay attention again. The -3 is multiplying by the square root. So to figure out your new ordered pairs, you just come multiply by -3. So what is 1 times -3? -3. So that means I'm going to go over 1, down how many? 3. Good. 1, 2, 3. Then when I go over 4, how many am I going to go down? Good job, y'all. Over 1, 2, 3, 4, down 1, 2, 3, 4, 5, 6. And you would connect them. We feel like we could graph them by hand.
Hold up, can you do that last dot one more time?
Yeah, babe. You agree the table we learned yesterday, the square root of 4 is 2, right?
Yes.
So normally with a parent square root function, you would go right 4 up 2. Well, this one's not going to go up, it's going to go down because I flipped it. But also, we can't just go down 2 because we're also multiplying by 3. So what is 2 times this 3 out front? That's stretching it.
6.
Yeah, so you start at your vertex, go right 4, and then we're going to go down 6 instead.
Okay.
Okay? All right, my Zoom babies, I'm going to keep it hot with y'all. Half of them in class got it and half of them don't. I can tell by their faces. So we are all going to try number 9. I'm pausing. Everybody try number 9. You have to graph it by hand. All right, y'all. So did we start the vertex at -4, -5? Hello? Okay, great. -4, -5. Fantastic. Where did y'all go next? Over 1, up 2. I love it because we're stretching it by 2. So it's not going to be over 1, up 1 like our table says. It's going to be over 1, up 2. And then what about the third point? Good. Over 1, 2, 3, 4, up 1, 2, 3, 4. So did y'all look like this? Yes? Fantastic. Any questions for me on square root functions? I'm going to throw in one more thing right now. If I asked you for number 9, I hope we're all paying attention. If I asked you for number 9, what the interval of decrease was, what would it be? What would you say? Interval of decrease. You see this graph going down anywhere? No. So would there be an interval of decrease? No. So you could write none. Does that make sense? Square root functions, listen to me, will not have both intervals. They either increase or they decrease because there's only one side to them. So you won't have both. So look, I want y'all to make sure you understand this. This one doesn't have an interval of decrease. You would write none. What about the interval of increase? What would we write? Just to make sure y'all understand these. Not -5. Where does it increase? -4 to positive infinity. There we go. -4 to positive infinity. So do we see how they won't do both? They're either going to go up or they'll go down. There's not going to be both because there's only one side. Do I need to show you another one? I'm going to. Some of y'all looking a little rough. All right, number 12, look at it. Is number 12 increasing or decreasing? Decreasing. It starts at the vertex and it points down. So everybody look, number 12. If I asked you for the interval of increase, what would you write? None. What would you say for the interval of decrease? Very good. Not negative infinity because it goes to the right. So, no, where does it start increasing? You look at the y's to see if it's increasing or decreasing, but when I ask for the interval, I'm asking you where. So remember, it starts at -6 and then it decreases on the right side, which means it goes to what? There we go. I'm glad we did this one. There are on your practice assignment tomorrow questions that also ask for intervals. I threw them up there because they are going to be on your test. But if you need more help with domain and range and intervals still, where do you need to come? Office hours. And tomorrow there's tutoring on it. Like I'm going to have examples where all you're doing is finding domain, range, increase, decrease, because that seems to be where we're struggling. Okay? All right, so I'm going to pause. We're going to get into our new notes. They are short. They are easy. My Zoom babies, y'all are going to love it. So page 28, last day of notes for Unit 3, Systems of Equations. All right, so review from Math 1. Who can tell me what a system of equations is? Uh-oh. Do you remember in Math 1 where you would have to graph more than one line at a time and then see where they crossed? That's a system. So a system of equations is two or more equations that have the same variables. And what you're doing when you're solving a system, you're looking to see where all the equations are equal. So on a graph, that would be where they all touch. Does that make sense? Yes? So in middle school, you should have learned, let's see, substitution, elimination. Great. We don't do them by hand in high school. You'll do them all in Desmos. That's the nice thing. But you definitely should have seen systems before. So this is two or more equations with the same variables. Y'all know what AKA means, right? Also known as, they can also be called simultaneous equations. So what did I just tell y'all we're going to be looking for with all of these? What will my answers be? Where they're the same. All the equations have to have the same variables. If I give you one equation, listen, I'm going to test your auditory learning. If I give you one equation that says 2x plus 3y equals 6, and then the other one says 2a plus 5b equals -12, those aren't the same variables. So you can't figure out where they're equal. They have to have the same variables. That's not what I'm asking. What did I say the solutions would be? I heard you say where they're equal. So on a graph, what would that mean? Where they intersect, where they touch. Very good. So the solutions are the points that the system has in common. So these are going to be the intersection points, which is where the two will be equal. All right, so before I teach you how to do these in Desmos, let's chat for a second. In Math 1, what kinds of systems did you deal with? I already told you earlier. Well, elimination is a way to solve a system. So Math 1, you should have learned substitution, elimination, and graphing for sure. And then some of y'all might have learned matrix method. We don't do that. Yeah, so, but what did I tell you earlier? Math 1, you graphed 2 what? I'm showing you with my hands. 2 lines. So in Math 1, you dealt with linear systems. What do you think we deal with in Math 2? Linear, quadratic, not exponential. That's in Math 3. You'll do that again in Math 3. What did we do yesterday? Square root. So in Math 2, you can have 3 different types of systems. You can have systems of equations that have linear functions, systems of equations that have quadratic, or systems of equations that have square root functions in them. Does that make sense? And they can also intermingle. So what we're about to talk about next is how many solutions we should have with each type of system. Okay? And then I will write down notes for how to do it in Desmos. We'll do like 2 examples, and then I'm turning y'all loose. Sound good? It's short. All right, so types of systems. My people at home, y'all unmute and ask if you got a question, okay? All right, in Math 1, we learned about 2 lines and finding where they intersect. So how many solutions could you have if I give you 2 lines and you're trying to find where they intersect? 1 or 0. Very good. So everybody look, I'm hoping you saw this in Math 1. I'm going to draw you 2 examples. First example, if your graph looks something like this, does everybody see how I have 2 lines and they intersect? Do y'all agree there would just be 1 solution? It would be this point right here where they cross. Okay. But you could also have 2 lines that don't touch at all. That says 1 solution, Hales. Yeah, I thought you were struggling with what it said. What kind of lines wouldn't touch? Yes, very good. I could also give you 2 parallel lines, and if they're parallel, that means they never cross. So how many solutions would you have? 0, none. So you would write no solution. I always abbreviate solution with SOL. SOL also means something else. Huh? Oh no, mine's a bad phrase that you shouldn't say. I'll pause and tell you. That's what your eyeball said just then. He was judging me. All right, 1 solution or no solution. Could you ever have 2 solutions with lines? No. If they cross, they're going to cross once, okay? So that's linear, linear. Now, you could also have a linear quadratic system. So with a linear quadratic system, let's think about it. That means we have a line intersecting a what? Parabola. Very good, Carter. So let's draw the different examples because there's actually quite a few for these. I could have a parabola that looks like this with a line that doesn't touch it at all. So no solution. Very good. And it's okay to get no solution. If they don't touch y'all, they don't touch. I don't want you freaking out thinking you did it wrong. That just means they don't intersect. There's no solution. There's no place where they are equal. What else could we have? 1 solution. What would 1 solution look like? Can you describe it to me? The line only going through 1 part of the parabola, but it has to be a specific part of the parabola. Yes, the vertex. If the line goes through the vertex, or what Sean just showed me, that's still through the vertex. If it was vertical straight down through the parabola, if the line touches the vertex, it will probably only have 1 solution. Okay, so I'm going to draw you a picture for that. it could look like this. And this is why we use Desmos for these, y'all, because, and I'm just going to draw a horizontal line, but it could also be vertical. But this is exactly why we use Desmos for these, because when you're doing different functions together, it can get really hard to find by hand if they touch once or twice. Does that make sense? So people at home, my advice on these is always going to be to zoom out on Desmos and make sure that it does only touch once if it looks like it, okay? And then how else could the line intersect the parabola? Twice, so like going through both sides, right? So I'm going to draw the parabola upside down now just so y'all can see different things. So like if the line cuts through right here, then this would be 2 solutions. Are y'all okay with linear quadratic systems? Okay. I'm not going to make you draw pictures for the rest of them, but I do want us to talk about the other kinds we could have. So you could have quadratic, which is 2 parabolas that intersect. If you have 2 parabolas intersecting each other, what do you think the options are for solutions? Think about it in your head. Think about the pictures. 0, because they could not touch at all. Like one could be up, one could be down, and they could have space in between, right? So that'd be 0 solutions. What else? 1 if what touches? The vertexes touch, good, and then 2. So if one looks like this, I'm not going to make you draw pictures, and then the other one looks like this. My hands are kind of fat and chunky. Let's see, what can I use? Chords. Fantastic. Let me get innovative. The ADHD is real. My husband looked at me the other day. He was like, what is wrong with you? I was like, I don't know, but you're stuck with me now. So it would touch twice. This is a terrible picture. I tried though. It would touch twice, okay? Or twice. Is it ever going to touch more than twice? Why not? Because why? You know, I have to ask you why. You're honors kids, I have to ask you why, because when you get to pre-cal and I ask you why and you can't answer a why question, it really makes me angry because it means your old teachers didn't push you. What if it's right beside it and they're both going up? They're eventually going to cross somewhere. 1 or 2. No. There's never more than 2. So what I'm asking is why? It's quadratic, which means what? 2 what? You're thinking of solutions as in x-intercepts. What'd you just say? There we go. If it's a quadratic, it has 2 sides, an increasing side and a decreasing side. It will only ever touch twice. You're not going to have 4 intersection points. You can try it, because I've tried it too. I was the type of kid that didn't believe my teacher and would try it until I could get more than 2. You won't. It'll be 2. So quadratic systems can have anywhere from 0 to 2 solutions. What's another kind of system you think we could have? Yeah, okay, so let's do linear first. You could have linear square root. How many solutions do you think that could have? 0 to 2. So let's think about it. A square root function, and we'll write that down in a second. I'm trying to make this visual for y'all though. A square root function is just a sideways parabola, right? But there are cases where I could draw a line through this and it could touch twice, right?
That's what I'm saying with the quadratic. If it's 2 U's, like that, you gotta go through twice.
2 U's beside each other will only touch twice. I'm gonna draw it for you. I get what you're trying to tell me. So we'll write that in a second. Linear square root is also 0 to 2, because remember, square root functions and quadratic functions are what? Inverses. Connor, you paying attention? All right. Square root functions and quadratic functions are inverses, correct? So they follow the same properties. So it will still be 0 to 2. All right, let me draw these U's for him before he has a heart attack over here. You mean one like this, right? And then you want the other one beside it? You can come draw it if you want. So I want you to watch. I see what you just drew. You drew something like this, right? Yeah? Okay. This purple one is wider than the blue one. So it's eventually going to end up touching over here. But since this blue one is skinnier and this one's wider, they're never going to touch on the other side. If you made this one skinnier, then this blue one would eventually touch the purple one again, but they will never touch more than twice. I can show you in Desmos if you want. All right, so linear square root, we say can have 0 to 2. What about quadratic square root like Carter just said? So think about it this way. What did the quadratic solution options, what were those? 0 to 2. So quadratic square root follows the same properties because square root functions and quadratic functions are inverses. So they have all the same properties, just the x's and y's are flipped. So it's also just going to be 0 to 2. Those are the 5 different types of systems you will see in math too. We don't usually do square root, but if you do see one, how many times could it touch? 0 once, or it could touch twice. Usually they do only touch once, I agree with you, but it's possible it could touch twice. People at home, any questions on this part of the notes? The only other thing we have to write down is how you actually do it in Desmos, and then we'll do 2 examples. People in class, any questions? I feel like some of y'all aren't with me. Keydreen, you with me, babe? Connor, you with me? All right. Y'all are good? Okay. People at home, we're good?
Yes, ma'am.
Okay, thank you. All right. So, steps for graphing and solving systems in Desmos. And after these 2 steps, we're just going to do 2, or not 2 steps, it's 4. But after these steps, we're just going to do 2 examples, and I will turn y'all loose on your homework, which you should definitely finish in class. All right, so your first step is you're going to type each equation. You could have 2 or more, so it could be 2 or 3. You'll typically just see 2 though. Type each equation in a separate box in Desmos. Separate box in Desmos. Spelling is not my thing. I gotta sound it out. I got kicked out of the, not kicked out, I lost the 2nd grade spelling bee because I spelled bananas wrong. I threw in an extra A and N. I was sad because there's a song for it. I'm probably too old to know the song. All right, once you have both of your equations into Desmos, and it could be 3, so once you have all 3, what are you looking for to actually solve the system? That boy said, yes, good, where they cross, right? So then you're gonna look at your graph. And determine all points where the functions intersect. So they may not cross fully, but wherever they touch, that is a solution. And then we've actually already done this a little bit when we did quadratic regression. Do y'all remember how you get the point to actually pop up in Desmos? You click it, yeah. So then you're going to click on that intersection point. And the solution is that ordered pair. So I lied, it's just 3 steps. I'm gonna pause and let y'all finish writing those steps, and then we'll do 2 examples. So here's example 1, copy this down. It says solve the simultaneous equation. Don't move ahead of me. I wanna make sure y'all do this right, because I don't know in Math 1 if all of you saw them written this way. So does everybody see how this isn't 2 separate y equals equations? Yes, we all see that? Fantastic. The way they have this one written, this would be called a simultaneous equation. It's not a system of equations, because how many equations did I give you? Just 1. But there's 2 different functions going on either side. So that's why it's called a simultaneous equation. If I give you a simultaneous equation like this, all you have to do in Desmos, Carter, are you paying attention, babe? All you have to do in Desmos, y'all, is split it up into 2 separate equations. So we can call this one y equals 2 square root of x plus 3 minus 2. And then this side we can call y equals 1/2 x minus 1 squared minus 3. So if I give you an equation written like that, it's just a simultaneous equation. You can break it up and make it into a system. So what I'm going to do is switch to Desmos. I don't even know if I have Desmos pulled up. I do. I'm so smart. Here she is. All right. So you go type each equation in. So y equals, the first one was 2. If you're looking for the square root, it's on the keypad. So square root of x plus 3 minus 2. All right, let me make mine smaller so I can actually see what's going on here. So I'm going to zoom normal. And then the other one was y equals 1/2 x minus 1 squared minus 3. Is everybody okay with this? People at home, are y'all okay?
Yeah.
Okay, so that's your system right there. This simultaneous equation, Sean, get off your phone. This simultaneous equation, if you graphed it, would be these 2 functions intersecting. So how many solutions do we have for this one? 2, and then to find them, what do? Click on them. Make sure you click the right points. Don't click that x-intercept right there. We don't care about that. So I want this intersection point and this one. And let's practice rounding. I want you to round to the hundredths. How many zeros does 100 have? 2. If y'all keep rounding wrong, I'm gonna lose my mind. I love you dearly, but we got to fix the rounding. So round 2 decimal places, which means 2 numbers behind the decimal. So that says 59, but what's behind it? A 6, a big booty. I did that just to see Henry blush. So what's it round up to? Negative 1.6, 0 technically, if it says hundredths place and wants 2 decimal numbers. So the first solution would be negative 1.60, 0.37. And then what would the second one be rounded, y'all? 4.61 comma what? 3.52. Very good. 3 52/100ths. That's all there is to it. You put the 2 functions in. If they give you 3, you put all 3 and see where they cross. Is everybody okay with example 1? I do not recommend going and typing it in yet because there's different ways you could type this one in that I'm going to show you, okay? And actually, I probably will just show you one way because I want to make sure you're doing it the way that'll work for Math 3 and Pre-Cal. Okay? I'm just making sure y'all are all with me. Everybody has it written down? All right, let's switch to Desmos. So, really quick, actually, before I switch to Desmos. Do y'all see how example 2, the first equation does not have an f of x? Some of y'all don't see because you're typing it in, and I already said not to type it in yet. It ain't just you. It was 2 other people, but they stopped early. All right, pay attention. Everybody look. If you type this in just like this, you may not get the same solutions as me. And here's why. I'm going to see if you all can catch it. Do these 2 equations have the same variables? What's not the same? Okay, the first one does not have an f of x in it, does it? Did everybody hear what Carter said? So listen to me very carefully. It doesn't have a y in it. If you type it in just like this, I'm going to be 100% real with you. About 50% of the time, it'll work. About 50% of the time, it does not work, and it gives you completely different solutions. You need to make them have the same variables before you go in and graph it. Does that make sense? So this first one is missing an f of x. So how could we write it so that it does have an f of x? What do y'all think? Huh?
Subtract the 1.
Ooh, say that again. Good job, boys. Set it equal to 0. Do y'all remember doing that in Unit 2A and 2B? So everybody look, I'm going to move the 1 over, and then I can put the f of x over here, right? So how would you move this 1 over? Subtract it. So everybody look, we're going to put it on the end, subtract it, and now this side I can just say is f of x because there's nothing over there. Again, you can be that kid that tries to defy me and go be, what's the word, rebellious. That's fine. It's going to work half the time, and half of the time it's not because I was messing around with it this morning to make sure. So I would highly recommend just making sure you set both of them equal to y, okay? So now I'm going to stop sharing. I'm going to pull up Desmos. And instead of, I think you actually can type f of x. We tried this the other day, but I'm going to type y instead of f of x. So the first one would be -2. We said it was x minus 4 squared minus 1. And then the second one is just 3x plus 1. Dang. Ooh. All right, so y'all look, this is a great example to do. I didn't even realize I did this. This is fantastic. It looks like they don't touch, right? Just to be sure, I'm going to turn my camera on so everybody can see my face. Sometimes the parabolas are wide enough. I hope we're listening because I see lots of clicking. This is why I don't like this unit because y'all just be doing your own thing. Sometimes the parabola is so wide that it will end up intersecting the line where you can't see it. So I'm going to zoom out. This parabola looks skinny though. Are these 2 ever going to touch? No, it doesn't look like it. So what would we write as the solution? No solution. You can say 0 solutions, but no solution. You could also see this symbol. Do y'all remember seeing this in middle school? That means no solution. Or you can write no solution. Or you can write 0 solutions. That's fine. I'll take any 3 of those. Do I need to do another one like that where you have to get them both set equal to y, or do we feel like we could handle it? Another one? Okay, let's do one more. People at home, are y'all good?
Yeah.
All right, let's do one more. If y'all aren't getting the same numbers as me still, I need to know, and I may have you share your screen with me later on so I can figure out what you're doing wrong. Let's do, there's a tricky one on the homework. That's fantastic. All right, let's do y equals square root of 2x and then plus 3. And then let's have the other one be x squared equals 2x plus 12. This is the last one we'll do. Then I'm turning y'all loose for real. We went longer, but y'all are asking really good questions and we're having good conversations. You'll still finish your work very quickly. All right, do these both have the same variables? No, what's missing? You pay attention, Evan? Okay. What's missing? Say it again, Chris. The y in which one? The second one. Do y'all see how the second one does not say y equals? If there was a y in it, let's talk about it. I need to see eyeballs. If there was a y somewhere over here, you could go ahead and graph it without getting it in y equals because it would have the x and the y, okay? Desmos will graph stuff with it not in y equals form. That's also another good thing about Desmos. But it doesn't have a y at all, so what do we need to do to make it have a y? Set a equal to 0, which means I'm going to move the x squared over to the other side and subtract it. Are y'all okay with that? So this would be y equals negative x squared plus 2x plus 12. And now do they both have an x and a y? Hello? Yes? They both got an x and a y. Fantastic. So now I can go graph them. That's the part where y'all will mess up, which is why I'm being so hard on you if you ain't paying attention right now. Because I just know somebody's not paying attention and they're going to ask me later, well, I got something different. I didn't put a y in there. Well, dang, that's why. All right. Square root of 2x plus 3. There's the first one. And then we just said y equals negative x squared plus 2x plus 12. Ooh, this was a great one too. How many solutions does this one have? Only one. I gave you one of every type. Wow. Sometimes you just get lucky. What's the solution to 2 decimal places? 3.70. Very good. 5.72. Do we feel like we could do that worksheet on systems of equations? Oh my God. I just had my hand had a seizure. Let's try that again. There we go. People at home, you feel like you could do your homework?
Yeah.
It's 12 systems. It really should only take you 12 minutes. I'm not kidding. Like a minute a problem. These do not take long. And there's really no shown work needed unless you got to throw in a y and get it set equal to 0, okay?